Thanks everyone for coming. So as in my other trainings that I've done here, I'm going to be using poll everywhere. So please go to this link, pollev.com/JonathanLars698, and I'll periodically post questions there where you can answer. You don't need to register for anything. So today we'll be talking about generalized estimating equations, or GEE, as it's probably more commonly known. So before talking about GEE, just want to do some review of generalized linear models because that's going to be the basis for GEE. So let's talk about GLMs. So I'm going to be using R as the computing software to talk about all this stuff in. So here I have GLM, the classic R function for generalized linear models. And I've just highlighted a few of the parameters for this function. So formula, family, and offset. Obviously, these are not the only parameters you're going to use. Data is also pretty important. But these are the ones that I just want to talk about for now. So formula, that's how we specify our linear model. What explanatory variables are we including, any interactions, polynomial terms, etc. Family is how we specify the distribution of the data. So most commonly, we're going to be using binomial or Poisson. What about offset? So if you navigate to poll everywhere, I'll activate this first question. What is the purpose of the offset parameter in the GLM function? Why do we have that? Wait, see if we get any other responses before addressing them individually. Okay, great. Roughly to model the exposure, this is excellent. Oh, a way to include a component. Okay, great. Okay, so yeah, I'm going to address this in very specific terms. So what does this offset parameter mean? Well, in Poisson regression, we can model the mean, like I've illustrated up here. Note that I'm using the canonical link function for the Poisson distribution, which is the log function, the natural log. So we can model the mean mu, or we can model a rate, which I'm going to call lambda. And since the mean is a function of the rate and time, or some measure of exposure, as someone put on poll everywhere, so we can go through this sequence of equations where if we want to model the rate, we can add in log of time or exposure. I've written that t is a measure of time here, but it could also be a measure of, for example, just like how many people are you talking about? So if we want to talk about rates of stroke, for example, in different census tracts, then we could talk about, well, how many people live in these census tracts? And that's going to be our time, so to speak. And what we end up with at the very bottom here is this, we're modeling the mean. On the left-hand side, we have log of mu. And then we have log of t is our offset, which is, it's like including an explanatory variable that has a fixed parameter value or a fixed coefficient of 1. So this allows us, if we're looking at, like I was talking about, the rate of stroke for different census tracts are going to have different populations. So we're going to want to include in our data how many strokes were there per census tract, and then also what is the population of each census tract, so we know, well, this census tract had a ton of stroke, but it also had a larger population. That's relevant to include. Okay, so this allows us to model the rate when we have counts and variable periods of observation or variable exposures. All right, so back to our GLM function. So I think it's really illustrative to look at the help page for family in R. It shows us all of our options. So like I said, binomial and Poisson are probably the most commonly used. But we also have Gaussian, gamma, inverse Gaussian, and then a bunch of quasi distributions. And we can see that for each of these distributions, we have a default link function. So in generalized linear models, we have this link function which connects the mean to our linear model. And there are canonical link functions for each distribution, or a canonical link function for each distribution. And those are the defaults here. So for the binomial distribution, it's the logit link function. So we use that for logistic regression. So hopefully this is familiar to people. What about if we take a look at this quasi? So not even quasi-binomial or quasi-Poisson, but just quasi. It has a default link function, which is the identity. That's also the default link function for the Gaussian distribution. It also has this variance parameter, and it says variance equals a constant. So what does this mean? So for each of these distributions, there's a relationship between the mean and the variance. So for example, for the Bernoulli distribution, the variance is equal to the mean times 1 minus the mean. We're probably used to seeing p times 1 minus p for the Bernoulli distribution, but p is equal to the mean for this distribution. So I'm using mu. And then for the Poisson distribution, there's a very simple relationship, which is that the mean is equal to the variance. So this is different from the Gaussian distribution, where the mean could be anything and the variance could be anything. They don't have to have a relationship. And so in linear regression, we don't assume that there is a specific relationship between the mean and the variance. But with other distributions, they have these relationships, so we should take those into account. And so that's going on behind the scenes for each of these distributions. It's not displayed here on the screen, but for the binomial distribution, the variance function is going to be mu times 1 minus mu. For the Poisson distribution, the variance function is going to be just mu. All right, so just to review, when we use GLM, we provide the formula, which is our linear model, the family, which takes care of the link function connecting the mean to the formula, and also the variance function connecting the mean to the variance. We provide an offset if necessary. All right, I have another question for you. Just activate it. What does quasi mean in this context? So we have quasi-binomial, quasi-Poisson, just quasi. How do we interpret that? Okay, that's no problem.
I don't remember.
That's okay. Maybe someone online can remember.
Yeah, it's on.
Maybe, okay, one more minute or so, see if anybody remember what quasi means.
Right. I remember. I remember correctly, but I was not sure.
All right. Okay, so this has stumped people. That's not a problem. We're going to talk about it. Oh, wait, did I get a response?
Yeah.
Oh, great. Okay. Not quite. Great. It's not strictly the distribution, but follows similar mean variance relationship. Okay, great. That is a great summary. Great. So let's talk about this. So sometimes the mean variance relationship is too restrictive. For example, with Poisson regression, what if our variance is actually just greater than mu? Yeah. So if that's the case, then what we would call that over dispersion. So we have a greater variance than would be predicted just by the Poisson distribution by itself. So we have to account for that somehow. We want to make our regression models more flexible. So we can make specifically the mean variance relationship more flexible by including a dispersion parameter. So I've called it phi here. And we're literally just saying, like, if we start with the Bernoulli distribution, instead of saying variance is equal to mu times 1 minus mu, we're just going to insert this phi and say the variance is equal to phi times mu times 1 minus mu, and do something similar for Poisson. So the phi is going to be greater than 0 because the variance needs to be non-negative. But it's going to be just any positive constant. So if phi is greater than 1, then we're going to allow the variance of y to be greater than what would be predicted by whatever distribution it's coming from. The result is that we're no longer talking about an actual distribution. So instead of maximizing a likelihood to estimate the parameters, we use a quasi-likelihood. So it's based on the likelihood, but we're sort of just inserting this phi in there to allow for over-dispersion. Yeah. So before moving forward, are there any questions about GLMs from anybody? anywhere. Feel free to put your question in the chat, or you can unmute yourself. Any questions in the chat? No. Okay. All right. Feel free to stop me as we move forward. Okay. So with GLMs, we assume the observations are independent. But what if that assumption is not appropriate for a certain data set? So this could happen in lots of ways, especially longitudinal data, hierarchical data. So in past trainings, in sort of this series, we've brainstormed ideas for how this might happen, but repeated measures is a classic example. Hierarchical data, people have provided examples of like, if you're taking samples from the same tissue, those samples are going to be correlated and not independent. Yeah, students within classrooms, et cetera, et cetera. So generalized estimating equations are a solution to this problem, and they arise out of GLMs. So that's why I spent some time talking about GLMs first. But now we can talk about GEE. So I'm going to be using for today this package GEE. It's not the only R package that handles generalized estimating equations. Another commonly used package is GPAC. But I'm going to focus on GEE and specifically the function GEE. So here are some of the main parameters for this function. So formula is the same as in GLM. It's how we specify our linear model. You can note here that as I've written this formula, I now have an I and a J subscript. So I indicates cluster and J indicates which observation we're talking about within the ith cluster. Family is almost the same as in GLM. The only difference is that GEE always estimates a dispersion parameter. It does that by default. So you could change it with scale.fix equals true if you wanted to not work with a quasi-likelihood, but work with an actual likelihood. But if you don't make any changes, it's useful to know that GEE is going to always use this quasi framework for estimation. Okay, what about ID? ID indicates cluster ID. There's also an ID parameter for when we were working with the package LME4, and the function was GLMER, if I remember correctly. So ID indicates cluster ID. So if you have repeated measures on people, ID might be the participant ID. If you have a cluster randomized trial, ID would be the cluster ID. If you have data on students in classrooms, ID would be classroom ID. In a previous session, when we had talked about generalized linear mixed effects models or linear mixed effects models, we could have sort of multiple levels of clustering. Based on my experience with GE, that I'm not sure how to implement that with GE. So for at least today, we're only going to be talking about one level of clustering. So not students within schools, within school districts, within et cetera, just repeated measures within people is what I'll be focusing on. And then we have this final parameter, COR-STR, that stands for correlation structure or working correlation structure to be more specific. And this is the within cluster correlation structure. So we're assuming that within each cluster or within each individual, observations will be correlated, usually positively correlated. And so we're going to tell R through this function GEE, this is what we think the correlation structure is. And I'm going to go into what our options are and what happens if we're wrong. I'll do that right now. So first, what are our options? So the first one is independence. So I've just put it here. This is an independence correlation structure. So along the diagonal, we just have ones because we're talking about correlations. On the off diagonal, we just have zeros. So we're assuming that actually within the cluster, all of our observations are independent. So this is actually the same as GLM. We're assuming that there's no within cluster correlation. So if you were to run GEE with an independence correlation structure, you should get the same exact thing as GLM. All right, that's maybe not super likely, although there are reasons we might want to check it or use it. So maybe one step up in complexity would be this exchangeable correlation structure. So it looks like this, where every off-diagonal element has the same correlation, same value, rho. So we're assuming that the correlation between any two observations is the same as the correlation between any other two observations. So this is one step up from independence, assuming correlation, but nothing too wild or crazy. Slightly more complicated, ARM. So AR stands for autoregressive. M indicates the number of previous outcomes to regress on. But the argument in the GEE function is actually MV. And the default is MV equals 1. So I'm just going to show what that matrix looks like. So here, again, along the diagonal, we just have ones because it's a correlation matrix. If we go one step off of the diagonal, we have rho. So if we're talking about the correlation between observations that are one step apart, whatever step might mean, we're assuming they have the same correlation. As soon as we go to two steps, we have rho squared. So these rows generally are going to be less than 1. So you can see that as we move, as we're considering observations that are further apart, the correlation is going to attenuate in this sort of classical, very regulated way. So for this to make sense, we want our observations to be equally spaced. But this corresponds to, like I said, autoregressive scenario. And observations that are further apart have lower correlation. All right, another more complicated one, stationary M dependent. So the default is for MV equals 1. So stationary is indicating to us that we have the same correlation for any two observations that are one step apart. M dependent means that observations that are one step apart are dependent on each other, but as soon as we get more than one step, the observations are independent of each other. So that's why the other off-diagonal elements are 0. So observations that are more than one step away are assumed to be independent from each other. And then this is the last one I'm going to present. It's not the last option, but I feel like I've gone through enough of these. So with unstructured correlation matrix, we're just assuming that any two observations have a unique correlation. And so we're going to estimate all of them. So this is the most parameters to estimate, but it's also the most flexible. And yeah, every pairwise correlation is individually estimated. So those are some of our options. So how do we pick which one is going to be best? And then what happens if we're wrong? So first, how do we pick a working correlation matrix? We can, oops, typo here. 22. So we can come up with some options. We can hypothesize what would make the most sense and just try it out. And I'm actually going to use a data example, and we're going to try a bunch of different options and just see what happens.
Sorry, John.
Yeah.
So let's say in the simplest one, the exchangeable, simplest one with a parameter.
Right.
Is this row an input of the function in GEE or not?
It is not an input.
Okay, so you don't need to assume anything from your data.
No.
Okay, got it.
There might be an option where you can give it a starting value.
No, I'm mostly worried about having to do that rather than not having to do, because it may get crazy when you have to estimate the row from the data. It's not really easy. Okay.
Yeah.
But if it's not input, okay, that's fine. Okay.
And then, okay, so we're going to try out a few. What happens if we're wrong? So the nice thing about GEE is that our estimators are still consistent and asymptotically normal if we pick the wrong working correlation matrix. That's why it's a working correlation matrix. It's our working hypothesis. It doesn't have to be perfect. And although if we choose the correct correlation matrix, then our estimators are more efficient. So there are advantages to being correct. But asymptotically, it all works out fine.
Sounds like get for loops here.
Yeah. Yeah. Okay. All right, so I do have an example. And I elected, instead of to sort of doing the example and putting the results in the slides, I actually just have pulled up, I'm going to do this in R.
Yeah.
So here's a description of our data set. We're going to be talking about the Indonesian Children's Health Study. Maybe I'll make this just slightly bigger, just in case. So we're talking about children who are preschool age, seen quarterly, so repeated measures. At each examination, we're looking at if they have a respiratory infection or not. And the main predictor was this thing, which is in our list of variables. It's listed as xerop, and it's short for xerophthalmia, or xerophthalmia. And what that means, it's related to your eyes, and it's a problem with your eyes that can lead to blindness if it's untreated. But the researchers for this study were using it as an indicator of vitamin A deficiency. So if you're deficient in vitamin A, xerophthalmia is sort of like a classic problem, disease that can result as that. And it's very treatable. So the good news about xerophthalmia is that if you see it in a child, you can give them vitamin A supplements and it cures this problem. They do need to be monitored because excess vitamin A is poisonous, but this is a solvable problem. So what the researchers for this study were looking at is vitamin A deficiency also a risk factor for just a respiratory infection? So infection is our outcome, and we have our main predictor that we're interested in is the xerophthalmia. But then we also have age. They included cosine and sine functions of time to try and indicate that we have this like cyclical nature of time for seasons. We also have gender. Height for age is a percentage of the National Center for Health Statistics standard, centered at 90, so a little complex measure of height. And then time, which is an indicator indicating which of up to 6 planned measures the row is referring to. So this might be easier to see if we actually take a look at our data. So I'm just going to load the data. And we can take a look at it. So here we go. We have our ID, infection 0 or 1. So clearly if our outcome is 0 or 1, we're not going to be using a normal distribution to model this. Or, I mean, maybe someone would argue that we could, but today we're not going to. Here we have age. Age was not in months. It was, where is it? It's in months centered at 36. Yeah, so that's why we have some of these negative values. Xerophthalmia is a 0 or 1. We have the 2 cosine and sine time variables, gender, height for age, and then time. So this is indicating which visit it is. So it could be 1 through 6. And if we scroll down, we will probably encounter some missing values. So like 1, 4, 5, 6. So this person did not go to their second or third visit for whatever reason.
Also, height for age is there, right? It's negative.
Yes, centered at 90.
And 90. Okay.
Yeah. Okay, so here's our GEE formula, or excuse me, our function. So I've already inserted arguments for ID and for data. I'm going to say that we have to use the binomial distribution. And so I was going to poll the audience. So Emanuele, you get to choose.
Gosh.
What do you want our formula to be?
So let's go back to the description. I don't remember.
Yeah, sure.
So let's say respiratory infection. I mean, you can put in whatever you like here, I guess.
Sure.
You have a lot of records, a lot of children. Let's try them all.
Sure.
I mean, and then we'll see what happens.
So perfect. Love it. Okay.
Yeah. Sorry, you have to type them all.
That's okay. I'll survive.
Cos T, sin T, what's that? That's gender, H for A. And time. Yeah, let's see what happens.
Perfect.
Oh, the correlation. Gosh.
Let's do a few options.
Let's try one. For sure, not in, I would say not independent.
Okay.
Site exchange will be 0 1. I don't know. This just need to try. See what happens.
Yeah, let's do this. And I'm also just gonna copy and paste this and choose some others. So for sure, I want to include an unstructured in there.
Okay. If you perhaps since you have 6 visits, perhaps well having the MR6. Maybe not. No. No, I don't know. No, let's try the first 2.
Sure.
Sorry.
No, it's fine. Maybe I'll do just ARM and see what happens.
Yeah, sorry. Yeah, ARM. I would think no.
Okay.
Yeah.
Oh, I have to make these differently.
Okay.
Okay, so we have same formula. Yeah, we got some errors.
Fatal error. All right.
Yeah.
Cluster size equals to 1.
Okay. So yeah, so like Emmanuel pointed out, we have a fatal error for our third correlation structure. So the third correlation structure is autoregressive.
Oh, and but cluster size equals to 1.
Yeah, so there must have been a child who was only observed once.
Yeah, okay. Yeah, that makes.
Yeah, so and the assumption for this ARM is that we have this autoregressive 1 model. And so there's, I guess, I don't know why this was a fatal error. It seems like the function could have just eliminated children who only had 1 observation.
But it did estimate some, right? It gave you an estimate.
So what it's presenting here is it ran GLM to get initial regression estimates. So I think those are the GLM estimates. Yeah. But anyway, the other 2 worked. So let's take a look at those. Okay, so this is mod 1. So as a reminder, our first model had an exchangeable correlation matrix. So you can take a look. Okay, so it's telling us some stuff we already know. The link function is logit. We're using the binomial distribution. So that's giving us the mean variance to mean relation. And then we used an exchangeable correlation structure. So here are coefficient estimates. So let's take a look at this table. So we're getting estimates in that first column. We're also getting a naive standard error and a naive Z, and a robust standard error and a robust Z. So first, we're working with the Z distribution, the normal distribution. So like I had said earlier, our estimators are asymptotically normal. So we're using this approximation, this standard normal distribution. The standard errors, we have a naive option and a robust option. So what is the difference? The naive standard errors are computed assuming that our working correlation matrix is correct. So it's just the computation, the formula for those standard errors is just to plug in our working correlation matrix wherever we need the true correlation matrix. The robust standard error, that's a sandwich estimator. So we're estimating the correlation matrix from the data and using that. So.
Very different.
Sorry?
They're not very different.
Exactly.
Very close.
Yeah. So that's telling us that we might actually be pretty good with our.
Yeah, we may have got it.
Exactly. So this is one way we can check to see if we've got a good working correlation matrix or a bad one. Bad one being if the naive standard errors were way different from the robust. That's an indication that we should maybe choose a different working correlation matrix. And then it has given us our estimated working correlation matrix at the very bottom. So you can see that all the off diagonals are the same. They're identical because we chose an exchangeable working correlation matrix. So it's using the same row or estimate of row for every off diagonal element. It's pretty low here, 0.0457. Yeah, so pretty low positive correlation. It's also, we're getting an estimated scale parameter. This is what I was referring to as phi. It's our dispersion parameter. for the Bernoulli distribution, if we were not using a quasi-likelihood, the phi would be equal to 1. Using the standard likelihood is equivalent to setting phi equal to 1. And we can see that estimating phi is actually not very far from 1. So there's not really that much over dispersion here. What else to say about these? Another thing to say about these estimates. So we are using the logit link function. These estimates can be interpreted just like in logistic regression. So if we exponentiate these, if we exponentiate the intercept, we get an odds. If we exponentiate any of the other ones, we get an odds ratio. And these are population averages. So if any of you were here or viewed or know about the generalized linear mixed effects models, if we're working with mixed effects models, the estimates have sort of weird interpretations because they're conditional on cluster. And that's a result of using these random intercepts or these random slopes. So we don't have those random intercepts or random slopes here. These are population averages. So we don't have to worry about conditioning on cluster membership. All of these coefficients can be interpreted as you would just in logistic regression. Yeah.
That's great advantage, I would say.
Yeah. Oh, yeah.
That's great.
Yeah, absolutely. Any other questions about these results? I'm about to show the results for our other correlation matrix, but okay. So looking at we'd also done
So yeah, you will need to, I'm always thinking in the perspective of reporting.
Yeah.
So you have to calculate the odds ratios and the p-values somehow to make them digestible to, say, the MDPI who asks you for
exactly.
your results. Okay.
Yeah. And yeah, thank you for pointing that out. There actually are no p-values provided here. I feel like that would have been we don't have to worry about degrees of freedom. We're using a normal distribution. I don't know why they don't automatically provide it.
Perhaps there may be some extra package that does it.
Yeah.
I don't know.
Yeah, you're probably right.
I'll ask Claude, see if they
Sounds good.
done something.
Okay, so here are the results for our unstructured correlation matrix. So is it giving us different estimates? If we look at the intercept, we have negative 2.8636. Up here, we had negative 2.89525. So slightly different estimates, but not super far off. It is giving us a different working correlation matrix. So for unstructured, every single off-diagonal element is being estimated. So you can see that all these off-diagonal correlations are different. So some of them are bigger than others. And in fact, we have a couple that are negative, although they're not super negative. So this might be something that as part of your data analysis process, you might want to explore. So for example, this is relative to the others, this is a pretty large correlation, and it appears to be between the 5th and the 3rd visits. So I don't know why that might be. These children are visiting some kind of health structure and getting assessed for respiratory infection. I don't know why there would be this high correlation or this negative correlation between the 3rd and the 6th. Potentially they're being treated. And so if they have a respiratory infection at one point, they might be treated for it before they're seen again. Not sure. So we get a working correlation matrix estimated. We get another dispersion parameter estimated, again, not far from 1. And then, like I was saying earlier, the estimates are interpreted just like in regression. So it's actually pretty straightforward.
Yeah.
Part of the reason it's straightforward is that I have not presented any of the theory whatsoever.
Yeah.
So yeah, I elected to do that because the theory behind GEE, yeah, it's a mess. It has so much notation. So if there's any curiosity on the part of people attending, I'd be happy to talk more about it, maybe in a future session or just like one-on-one, but it just was not worth trying to include all of that into today's talk.
Okay, Jonathan, there
Yeah.
is actually an option
Oh, okay.
for getting p-values in package, according to Claude AI, package GEEM capital M, where it says modern GEE implementation with matrix-based computations often faster than GPAC.
Oh, okay.
GEEM. I don't know, maybe.
Cool.
Yeah.
All right. So
It looks like it gives the p-values,
great.
maybe useful.
Yeah. So yeah, this is definitely not, GE is definitely not the only package. So
Yeah, it also lists GESMV, GEE with small sample corrections for sandwich variance estimators. I don't know. And MALT-G for multinomial responses in GEE models.
okay.
But they need to be tried out.
Sure. Yeah, and actually, so that highlights that GE doesn't have a multinomial distribution. So if we look at
All right, so I guess that makes up for that.
Yeah.
MALT-GEE. And it looks like also that one gives the p-value, but
okay,
I'm just relying on the list
sure.
that I got from the AI.
Yeah. So this is the help page for GE, the function I've been using. And if we scroll down to family, we can see that there are only some families that are supported. So we have Gaussian, binomial, Poisson, gamma, and quasi. So those correspond also to distributions that are available for GLM. So some links are not currently available, as you can see here. The inverse Gaussian variance function is not available. But so other packages are going to be maybe more flexible than this one and have more options for you. Okay. Just going to leave an opportunity. Any questions about this example or the results that we got before moving on? Okay. Great. So that was our example. I just wanted to reiterate some things. Oh, diagnostics. Okay, so like I said earlier, the naive standard errors are computed assuming the working correlation matrix is correct. Robust standard errors are computed without making this assumption. So if they're approximately the same, our working correlation matrix is approximately correct. I'd already said that, just to reiterate. We can also examine the unstructured correlation estimates to get a sense of what working correlation matrix is best. So if we estimate all of them and they seem to be pretty similar, we could simplify our model and use an exchangeable working correlation matrix. What about diagnostic plots? So this is the bane of my existence. It's hard to find good advice. I did find this one paper, so Carrier and Park from 2008. And it's brought it up here. Oh, it's right here. So it's in the journal Computational Statistics and Data Analysis. They do offer some recommendations for residual plots. There are some issues. So my reading of this paper was they sort of said, well, this is how it works for a normal distribution. So let's just do the same thing for these other distributions. And my memory of this paper is that they don't actually provide a justification for why it should be the same, but they do provide some simulation studies. But they only provide simulation studies for when you have balanced data. So the same number of observations per cluster. And that's not the case for the data that we have here. And that's not going to be the case for every data set. Maybe even not the case for most data sets. So we have some limited advice, but it is just generally difficult to find advice about diagnostic plots. But I'll post this. So I'll post this for those of you who are in the data science department. In the training shared drive, I will post this paper so you can check it out, and also the slides as well. I'll also say, since I'm on the topic, I've already posted a different data example, and two are Markdown files. So one, our Markdown file is me going through that data example step by step. And the other one is me asking questions and just in like blank chunks. So if you want to go through a data example on your own, you can use the R Markdown file that has all the blanks, do it yourself, and then you can take a look at what I did and see if you agree or disagree. Yeah, this is reiterating what I had already said about that paper. So also when it comes to model selection, GEE uses quasi-likelihoods, not likelihoods. So we don't have likelihood-based methods available to us for model selection. So I would love it if someone could tell me more about best practices for diagnostics and model selection. I just don't have much to offer today, unfortunately. Interpretation, this is just reiterating what I had said. Coefficients in GEE are always marginal to cluster membership, meaning we're averaging across clusters. So we're working with population averages. We can interpret the coefficients as in generalized linear models. All right, what about choosing between GEE and a mixed effects model? So I can offer some things to think about. So GEE is semi-parametric. We are assuming the mean model and the link function. We're essentially estimating the mean variance relationship. There's like a base to it that we are assuming, for example, for Poisson regression, that the variance is equal to the mean. But then we're also estimating this dispersion parameter. So that makes it more flexible for us. We're not assuming, although we are providing to GEE or any other function, we're providing a distribution. We're using quasi-likelihood. So we're not actually assuming that it follows a certain distribution. So it's semi-parametric, whereas with mixed effects models, it's fully parametric. We are fully assuming that we know the distribution of the data. So something to consider. GE makes fewer assumptions. Mixed effects models, we're assuming we know the full likelihood, aside from some finite number of parameters. And for GEE, the coefficients are interpreted as averages across clusters, population averages. With mixed effects models, the coefficients are interpreted as conditional on cluster, which is something we talked about last time and gets pretty confusing. So just things to consider as you're making a decision about which of these to use. What assumptions are you willing to make, and what kind of interpretations are you looking for? All right, what's next? I would say the next question is, what about if you have missing data? And methods are going to differ for these two approaches. So this is going to have to wait for another training session. Unfortunately, I don't have a full discussion of this prepared for today. I can give you some spoilers. For GEE, sort of a good method to use it is inverse probability weighting. So I can talk about that at a later session. For mixed effects models, one method is pattern mixture models. Yeah, Manuel is making a face. Yeah, they're complicated. Maybe not something we want to deal with. But anyway, so this is all to say that I definitely plan to talk about missing data for longitudinal data at a future training session. The data is TBD. My schedule is pretty booked for a little while, so it's going to be a moment before we can talk about this, but it's definitely on the docket. All right, so these are the references that I used. Please fill out the evaluation that will be emailed to you soon after today's session. And pause for questions. That's actually all that we had covered today. So any questions about any of that?
We have a question in the chat. Yes. I find many clinical journals dislike the use of GE. Any similar experience?
Wow, I have not heard of that.
So, Erica, what was the question?
I find many clinical journals dislike the use of GE. Similar experiences.
Well,
Huh, yeah,
because they don't know how they work.
okay. Interesting.
So you haven't had that experience?
No. So to answer the question simply, no, I have not had that experience. I'm very curious why they would not like GE. Yeah, maybe it's that they don't understand it.
Yeah, like, I don't find them to be very commonly used, I have to say, from my experience. I don't know. Do you
Yeah.
find them often? I don't know.
No, yeah.
Right.
When it comes to actually like reading the literature, I find that the mixed effects models are far more common.
Yeah, mixed effect models are more.
And I think that might be because of understandability, that it's sort of, it can make more sense if you're saying, oh, random intercept. Each of these clusters will have its own intercept.
Yeah.
That sort of makes sense. Whereas with GE, it's like, what is going on? Unbiased estimating equations? I don't know what those are.
But Jeff, inference should be easier, right? With the GE, I'm responding to Jeff's.
Yeah, I think it's inferential.
I mean, it looks like inference for GED, it's more straightforward.
Yeah, you're just normal distribution, asymptotic, everything's
That's
asymptotic.
why I said they don't know how that works. I mean, I'm just guessing.
Yeah, not sure, but I'd love to hear more.
Really don't know.
We do have another question in the chat. Do time intervals have to be consistent?
Okay, great. So I'll repeat that. Do time intervals have to be consistent? They do not. They do not strictly need to be consistent. Maybe if I go back. So for some of our correlation matrices, they're only going to make sense if the time intervals are consistent. For example, autoregressive.
Yeah.
So for this one, we want our observations to be equally spaced, so that the difference, so here I use my cursor. So like here, this row square that I'm circling right now with my cursor is the correlation between the first observation and the third one. So we're assuming that's going to be the same as the correlation here between the second observation and the fourth. So those distances between those observations need to be the same for this to make sense. So for some of these correlation matrices, we do want equal distances between steps, but it's not a requirement. So for example, it might be the case that you would use an exchangeable correlation matrix, even if your observations are like unevenly spaced. And actually, in the example that I posted to the shared Google Drive, it's a trial of Progabide as a treatment for seizures, for epilepsy. And they had intervals that are not equivalent. And it turned out that, I think if I remember correctly, exchangeable tends to be just the best fit to the data. So, you don't have to have equally spaced observations for these to make sense. And also, like, for this unstructured matrix, this is not assuming that any two correlations are going to be the same. So arguably, this would be the most appropriate if you have some like wild, yeah.
I have another one.
Great, perfect.
Is there any rule of thumb on sample size or number of variables that we need for meaningful model?
That's a good question. Not that I know of. So my advice would be to run some kind of simulation study to do sample size calculations. What I can say broadly is that because this GEE is semi-parametric and it's relying on these asymptotic results, you could argue that this is going to be maybe a larger sample size method. Whereas with the fully parametric mixed effects models, we're making more assumptions and maybe we'll have more power based on those assumptions. But I don't have any sort of rules of thumb in terms of like number of observations or number of clusters versus number of variables that you could include in the model. I guess I could say that so these asymptotics that we're talking about, where we're relying on our estimators being asymptotically normal, that asymptotic refers to the number of clusters. So you can increase in hierarchical data like this, you can increase the number of clusters and or the number of observations per cluster. So it's in terms of our coefficients, and estimating those with more precision, we're going to want more clusters. But to answer your simple question, or to answer more simply the question, I don't know of any rules of thumb as of right now. Any other questions? Okay, cool. So I would say, please fill out the evaluation. Also, if actually, let me just check who we have here. Okay, so I want to say two things. The first thing I'll say is please fill out the evaluation. If you want, if you have requests for more stuff to cover, whether it's within GEE or more broadly within longitudinal data, feel free to put those in your evaluation, because I will definitely take those into account when planning new trainings. The second thing that I'll say is, for the last session, someone did say in their evaluation that they were so confused about the interpretation of coefficients for mixed effects models. So I can go over that again. I brought up the slides from the last training session. I can talk about interpretation if there's interest, but if people are thinking they just would rather go about their merry way, we don't have to talk about that. So maybe, I don't have a poll everywhere question for this, but if you're interested in revisiting interpretation of coefficients for mixed effects models, maybe just put in the chat that you are, and we can just see if anyone's interested. Stickers? No. Okay. All right, that's fine. So yeah, if you have any follow-up questions, feel free to put them in your evaluation form. Come see me, send me a message on Slack, send me an email, whatever. And we can end there. Thank you.